Okay, I think I'm going to start with the last question first, and I'm just going to talk to you a little bit about this because you just have to kind of know this. This is like a famous joke in mathematics. Okay, so the harmonic series diverges. I'll tell you one of my favorite stories. In grad school, a fellow grad student told this story that whenever he taught calculus, he would just tell the students, there's going to be a quiz on such and such a day, and it's going to contain one question. Does the harmonic series converge or diverge? And the answer is the harmonic series diverges. Okay, that will be your quiz. And he would always get people missing the quiz. So there you go. Harmonic series diverges. What is the harmonic series? It is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. Why am I going out this far? And why won't I stop? Well, because I'm going to stop at 16, and you can figure out why. I'm going to tell you why. If you group them like this, here are 8 terms, all right? And you replace all the terms except 16 with 1/16. You're replacing all the terms with something smaller. This whole bundle now is 1/2. So that means if you put the terms back the way they belong, this is going to be larger than 1/2. Okay, and you can do the same thing downstream with a group of 4 items. So this group of 4 items is greater than 1/2. This group of 2 items is greater than 1/2. And you may as well put these guys together. It's kind of unfair, but anyway, every subsequent bundle is going to be twice the size of the previous bundle. So group of 4, 8, 16, and so forth. This demonstrates that no matter how far you go out, you can grab another bundle which adds another half to the total sum, which means it's never going to stop growing. It's just going to grow slower and slower and slower. But if you have patience, you can always add another half, which means you can always add another 1, which means it will never stop growing. Okay, I will leave it to you to use the integral test for that same problem, but I'm going to use other examples to talk about the integral test. I'm going to just start with just a generic picture. If I have a series, I'm imagining it almost like backwards Riemann sums, right? So Riemann sums, you add up a whole bunch of little boxes to approximate an integral, but what we're actually doing now is we're using an integral to approximate a whole bunch of little boxes. So if this box represents a width of 1, okay, so this is a width of 1, and it's the height of whatever series, the first term in the series. So this is the first term in the series. Okay, then we're going to have another term. It's got to be decreasing. Second term in the series. All right, and we're going to do like the third term and so forth. And I'm going to have to pause this a little bit to get a picture up here. If you integrate the function that generated this series, the function itself, you're probably imagining, goes through the middle of these bars, and you can't even tell if that integral is going to be an over or an under approximation to the thing you're trying to determine whether it converges or not. So you may think initially, well, this is crazy. How can I use this integral to make an approximation to whether or not this thing converges? Okay, fair enough. But here's how. We're going to actually make an under and an over approximation. I've attempted to draw a blue curve as an under approximation and a green curve as an over approximation, and that dotted red curve is probably what you're visualizing on first pass as to what it is we're trying to calculate when we calculate the integral of this expression. But the magic comes when you realize that it's the same integral but just shifted over. So even though maybe we're starting here, this blue curve is going to be the same as the green curve shifted. So, for example, this blue curve from 1 to infinity is going to have the same integral as the green curve from 2 to infinity. Okay, they're the same picture. So then what we're going to say is, okay, fine, the actual sum is somewhere between the green integral, but that would be from 1 to infinity of the green, is the green is going to over approximate, the blue is going to under approximate, but these two guys, we know they're just off by the height of that first bar. That is the difference between the blue and the green. So this integral either converges or it doesn't. That one bar isn't going to make a difference between whether it converges or not. And it also puts a bound on the actual sum, because we can over approximate it and we can under approximate it. And if both of those integrals converge, we're good to go. So let's ask a question. What if the series itself is like this? If we're going to use a summation symbol instead of writing out the terms, n is equal to 1 to infinity, and let's put something in here, e to the minus 4n. That's our series. Okay, does it converge? Does it converge? And of course, we're not asking what does it converge to, we're only asking does it converge. So you can calculate e to the minus 4x, and this bottom number is not really that relevant. You could start further on if you like. And the question is, does this thing have an actual value or does it go infinite? If it has an actual value, then the original series must also converge. So let's go ahead and see if this is going to work. I'm going to be a little sloppy, as I usually am with my notation. Let me make sure that I took the derivative right, the integral right, by taking the derivative to get backwards. E to the minus 4x should give me itself back, but it should kick out a negative 4, which will cancel the negative 1/4, so it looks like we did this correctly. Okay, so now I'm going to go ahead and sort of write this again in my sort of sloppy notation. Plus 1/4 e to the negative 1, and this thing goes away, and this thing is fine. It's still positive. It's kind of usually good to make sure it's positive. If it's negative, you probably made a sign error somewhere. That should be positive because you're approximating your series, which is purely positive. Okay, so that's good. So it's equal to, this integral is 1/4e, and it's kind of in the same ballpark as the series itself, but it's not exactly the same. Okay, it's not. So we're not saying they're equivalent. We're saying, just typing this so that it's legible. We are not claiming that this value that we just found is equal to the series. We are simply saying that either both or neither converge. They have the same convergence, yes or no, but it doesn't tell us the value. Again, I should give you a picture proof that kind of shows you can put an upper and lower bound on the series, but this isn't something that we need to do right now. Okay, just when you thought it was safe to go back into the water, right? Just when you thought you understood the difference between sequences and series. What is going on here? What is a sequence of partial sums? So, if your series looks like this, a plus b plus c plus d plus e plus f, and so on, the sequence generated by adding a piece and then another piece looks like this: a plus b plus c, a plus b plus c plus d, and so on and so forth. That's what's going on. You just keep adding one more piece, one more piece, one more piece. And so if you're asking for capital S3, that's just going to be a plus b plus c, right? Capital S of capital N, like the sequence, the nth term in your sequence is just going to be sum of your term. So I'm going to use a little s for this. Little n goes from 1 to your capital N. You're just going to add up the first capital N of those. Okay, that's all it's saying. So it's just a notational convenience. And you may ask, if the sequence is converging, you can ask, is the series, the sequence of partial sums is converging if the series is convergent. Okay, so just be careful about the anatomy of these things. Just use the right words for them. And one last little concept about something we call telescoping series, or series that alternate signs. Okay, so this would be a conditionally convergent situation. And I like to just talk about conditional convergence. If you have a big pile and it adds up to the number 10, and another big pile and it adds up to the number 3, negative 3, and you add them together, you're going to always get the number 7, always, no matter what order you add up the pieces in, because you're just going to get to all of them eventually. However, if you have a big pile of infinity and a big pile of negative infinity, you should think of one of them as being a hot water spigot, and the other one as being a cold water spigot, and it's coming out of the same nozzle, and you can make any temperature you want. You can make that water come out any temperature you desire. If your hot water is 150 degrees and your cold water is like 30 degrees, you can make any temperature between 150 and 30 by just adjusting the speed at which you're letting the water flow through your faucet. Okay? As such, when you're doing these problems, the order of the terms matters, and you have to require that you have to take them strictly in the order in which they come, otherwise these rules don't work. Okay, so then if you have something where 1 over k minus 1 over k plus 1 has been combined into a single fraction, then it allows you, if you allow this thing to happen, then what we get is we have essentially a piece out of the alternating harmonic series. And we're going to add up those pieces. It's going to be 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. And all the positive pieces would add up to positive infinity, and the negative pieces would add up to negative infinity. And but because we're allowing this sequence to be followed, and we're allowing this this simplification to take place, then this is going to cause the alternating harmonic situation to go ahead. Alternating harmonic series will actually converge. Will converge conditionally, and the condition is the order must be maintained. Okay, so you can go ahead and figure that out yourself, and I guess I will see you on the next video.